today to introduce Rick Anthes as our speaker today. I don't think I have to say too much about him, but I will anyway. Rick, amongst many things, of course, is the father of one of the world's most widely used mesoscale models, the Penn State NCAR model, mesoscale model. And, of course, he's known as long-term president of UCAR, now president emeritus. Just let me give you a little bio for Rick. Following his PhD at University of Wisconsin-Madison, Rick moved to Penn State in 1971. I'm not quite sure where he actually started this work at the model, whether it's in Penn State or at NHC before. Miami even before that. So he spent some time even at Miami. And then 1978, he became a full professor. In 1981, Rick moved here to NCAR, where he took on the role as director of the NCAR's Atmospheric Analysis and Prediction Division. And in 1986, he became director of NCAR, and in 1988, became president of UCAR, where he served till 2012. So that is really long-term president. He has published over 100 peer-reviewed articles and has won the AMS Clarence L. Meisinger and Jewel G. Charney Awards. He was president of the AMS in 2007, and in 2015 he was presented the highest award of the AMS, the honorary AMS membership. But Rick still remains quite active in research, and in recent years he became interested in the radio occultation observation technique. Rick was one of the key players in the highly successful GPS MET experiment, as well as the successor COSMIC, which is a constellation of 6 satellites that was launched in 2006. And I guess his talk today addresses that in a fair detail, but not just GPS occultation, but some other data sets as well. So please let us welcome Rick for his talk, Estimating Observation and Model Error Variances Using Multiple Data Sets. Rick, please.
Okay, thank you all for coming on a turn this on, I guess, on such a cold, snowy day. I never would have thought when I was working on MM5 that I would ever get into satellite meteorology. And when I was in satellite meteorology, or when I was president of UCAR, I never thought I would be a scientist again. And when I left UCAR as president in 2012, I figured I'd never give a scientific seminar to EOL, which is an observational laboratory and a very famous one. But here I am, which just goes to show if you live long enough, you can do a lot of different things. And anyway, so this is interesting. I think you'll find this interesting. Let me just introduce it here. Supposing you have multiple data sets, all supposedly measuring the same thing of a variable at the same location and time, for example, temperature. And the question is, how can we estimate the error characteristics of each data set? So you might have radiosondes, you might have dropsondes, you might have passive infrared sounders, you might have passive microwave sounders, you might have radio occultation sounders, you might have aircraft observations, but you need a lot of them. And you might have several models. In this method, you can combine any of these data sets in different ways, the models or real observations, and estimate the error variances of each system. And it seems a little bit magical, but we'll see how it actually works. Now, there are at least 3 ways that I was able to find to estimate the error variances of observations. And one is the apparent error method. Has anybody outside of radio occultation heard of that? It's not a very well-known method. It's called the apparent error method, and I'll show a slide on that later. And then there's the 2-cornered hat method, which is a name that Therese and I came up with, and I'll talk a little bit about that, but she will talk more about that on Friday. And then the 3-cornered hat method, which is the focus of this talk. And so in this talk, we're going to compare 5 co-located data sets to estimate the errors associated with each data set. And the data sets are radiosondes, radio occultation, and there will be 2 variations of radio occultation, retrievals for temperature and water vapor, the ERA-Interim reanalysis produced by the ECMWF, and the operational INSEP global forecast system analysis. And all of these data sets were in the year 2007 in the tropical West Pacific and the subtropical West Pacific. So my advertisement is that Therese is going to give a closely related talk at a cosmic seminar computing RO error variances, the 2-cornered hat and 3-cornered hat method for simulated and real data. So she'll be digging into the properties of these systems in greater detail than I'll have time with today. It's this week, this Friday, FL4, 3rd floor, 11 o'clock this Friday. So come and see that if this strikes your fantasy. Okay, a little bit of history. Now there's an interesting side story to this whole thing that I'm going to relate to you. Actually I found a fascinating history of science. This 3-cornered hat method was introduced in 1974 by physicists Gray and Allen at the National Bureau of Standards at that time, and they were estimating the frequency stability of individual oscillators, cesium clocks. And this paper was presented at an obscure conference in Atlantic City in 1974, and that led to several papers later in various publications where they used the same method to compare the accuracy of GNSS clocks from multiple clocks. In this paper, they used the same method to look at the load deformation from gray satellites, ground GPS, and GCM models, so looking at essentially gravity variations. And then Aaron Griggs over here at CU, in a couple of papers, very recently, 2014, also looked at GNSS clocks, compared them using multiple clocks, and Luna et al. In the Geophysical Journal International also using GNSS clocks from multiple clocks. So they're looking at clock errors, trying to estimate the errors of clocks using this method. All right, so that's all of these papers lead from this paper. Then there is another method called the triple collocation method in 1998. And this paper was by Ad Stoffelen, who is at KNMI now. He looked at scatterometer winds, ocean surface winds from buoys, and the INSEP model surface winds over the ocean. Those were his 3 data sets. He called it the triple collocation method, and a bunch of papers followed his, going down through here. I'm not going to read them all, but all of these papers reference Stoffelen, but not Gray and Allen. So there are 2 separate threads here. And this group didn't know about the other group, and the other group didn't know about this group. So then Risa and I rediscovered the wheel in 2017. Therese gave a seminar in Cosmic on the comparison of multiple data sets over the tropical Pacific. And John Braun was there, and he said, you might think about using a method that I used in 2001 to actually to estimate the error variances from these multiple data sets. So in August, I fooled around with the equations for a long time and actually derived the 3-corner hat method. And Risa computed the first results using 4 radiosonde stations in the Pacific, Guam, and 3 Japanese stations. And we reported them in September. This is Risa, this is Shay Gilpin, who is a former SOAR student, and both of them working with me, and we're debugging their programs, because of course I never made any coding errors when I was coding models, and so the bugs were all their fault. If you believe that. Okay, so we had these results. And on Sunday, there was a 8-day Cosmic International Working Group on Radio Occultation workshop in Estes Park. And they gave us Sunday off and Sunday was a terrible day, cold and wet and snowy, and so we invited these people to hear two papers, Shea's results on a different topic, which I won't get into today, and Reese's results on this triple collocation or three-cornered hat method. And we had some pretty good people here besides us. There's Ian Culverwell at the UK Met Office, Eric DeWeaver, a program manager at NSF, but a very fine scientist, Sergei Sokolovsky, one of the best-known radio occultation scientists in the world, Sean Healy, an expert in numerical weather prediction data assimilation, Uli Folsch, who is actually Reese's PhD advisor in Graz, and Andrea Steiner, a colleague of Uli's and Reese's in Graz. And these are all experts one way or another in data sets. So we gave Reese gave the talk, earlier version of the one I'm giving today, and there's a lot of interest among these groups. There's also a lot of skepticism because the results looked too good. They looked kind of like magic. Nobody had ever heard of this method before, from either the Gray and Allen stream or the Stofflin stream. So, going on with the history, in October and November, we wrote a draft paper showing the detailed derivation and results, and we shared it with these people and with other experts in NWP and RO. And in December, Sergei, who was one of the friendly reviewers, said, this looks similar to the method Aaron Griggs used to estimate the errors of GNSS clocks. And this actually led me to the discovery quote of the Gray and Allen paper, because I read her paper, and she referenced Gray and Allen going back to 74. So, okay, the good news is I have a pedigree or a heritage of people using this method. It's not just something crazy that we dreamed up. Bad news is we didn't create anything original. We reinvented the wheel. So we put this reference into the paper and submitted it to Atmospheric Measurements Techniques with references to the Gray and Allen and subsequent papers. Now, one of the ironies of all time, within hours, they assigned to Associate Editor Ad Stofflin, who, you remember, discovered this method in 1998. And he responded within hours with this kind of well, you can read it. It sounds kind of arrogant to me. This was a quote in his review. The development in this manuscript is very useful indeed, but it is so useful that similar methods do already exist since already a few decades in the scientific literature. For this reason, the author should link their contribution to the state-of-the-art literature in their field before the review process. Triple collocation was first employed by me last century. Geez, I'm 100 years old, and I still haven't read this goddamn paper. Triple collocation at ECMWF for wind observations, but since then widely used for wave, sea surface temperatures, ocean color, soil moisture, leaf area index, and precipitation. Okay, so he got me. But the amazing thing is, he, of course, had made the same mistake in 1998 because he didn't reference Gray and Allen or any of the papers that came after that. So he rediscovered the wheel too. And when I pointed this out to him, he was just a little bit apologetic, saying, yeah, you're right. Everybody makes a mistake. But at first, it was all huffy-puffy. So anyway, what are the chances of getting your paper submitted to the only guy in the world, in the international community, that's done the same method before? Anybody else would never have heard of any of this. So anyway, reference his papers, and that's so resubmitted the paper in January, and it's still out for review. Okay, so now you all love long math derivations on late afternoons, right? So, but here it is anyway. And let me just start out with an interesting equation that's actually fairly profound anyway. It raises a lot of thoughts. Let's define the error variance of a variable x for example, temperature, specific humidity, relative humidity, refractivity, as the summation of x minus true squared divided by n. So x minus true is the error of x. So that's pretty easy. And however, so true is the true but unknown value of x, and the summation is over n samples. And the n samples turns out to be very important. You need a fairly large number of samples for this method. But what is true? This is a very philosophical question, actually. What is truth? If you look at Google, what is truth? You get tons of philosophy and religious argument and all kinds of stuff. What is truth? So what is truth? Well, this is a famous example of what is truth. This one I actually like quite a bit. I found this on the web. This is an object that the orange light shining from here, and you get this image. The blue light shining from here, you get this image. So these look very different, right? If this is all you see, you have to think before you come up with this as the truth. So this is true, and this is truth. I told you could get philosophical here, right? So what is true in our case? I'll leave that to you. But going back to this equation, this is the equation that we'll start with for all the different data sets. And true is probably the closest thing I can come up with to is kind of an average over a volume, about 50 kilometers on the side and a few hundred meters in the vertical, some sort of average. So it's, but I'm not going to get into that. So let's start with that equation. Let radio occultation, RO, correspond to x of RO, or the value of x as estimated by radio occultation. Let's let ERA correspond to x ERA, or the value of x is estimated by ERA, and similarly for GFS and the radiosondes. So we'll just use RO, ERA, GFS, and RS for the symbols for the different variables.
What's ERA?
ERA-Interim. It's the reanalysis from ECMWF. It's a very useful research data set, because what they do is they use a state-of-the-art model and they assimilate every single observation globally they have, and these observations have been quality checked, and they do this in a research mode. And so it's probably the closest global analysis to truth that you can get, because they use all the different observations and they have estimates of all the errors in the observations. So ERA is the reanalysis. Now this is the part that you always hate when you read a paper. You go from that first equation to, and this is what they thought at the workshop in Estes Park, I think, because they didn't have time to read all this. And this does look kind of like magic. Easily shown that, well, there's 6 different equations for estimating the area variance of radio occultation. Here's one of them. The area variance of radio occultation is equal to 1/2 the mean square of radio occultation minus ERA plus the mean square of RO minus GFS minus the mean square of GFS minus ERA. So here's the 3 data sets. RO, ERA, and GFS. And they're combined in different ways. The differences are combined in different ways to get this estimate. And then you have error covariance terms. Error covariance between RO and ERA, error covariance terms RO and GFS, and error covariance term of GFS and ERA. So this just says that if the errors of any of these systems are correlated, these terms will be non-zero. If they're uncorrelated, if the errors of radio occultation are not correlated with the errors of ERA, then this term goes away. In fact, the key to this whole derivation is that these error correlation terms are neglected, because you don't know what they are. Okay? So these are the 6 equations. Variance error of RO is equal to all these different combinations. And you can get that from that first equation, variance error of RO is RO minus true. And then adding and subtracting and moving the Ponzi things around and playing, and truth cancels out, so you don't really need to know what truth is because it all cancels out. And anyway, it's high school algebra. That's all it is. It just takes a long time to get these things correct. And then Visa has to code them and not make any mistakes. So there's the 6 equations for RO. Okay, some of you might want a little more detail, so you asked for it. Here's just an outline of some of the gory details to derive those 6 equations. You start out with this. RO minus ERA is RO minus true minus ERA minus true. And you're just adding and subtracting true to this equation, so nobody can argue with that. Then you square it, and you sum the squares, and you get this equation, and you can get similar equations for all these other differences. RO minus ERA, RO minus GFS, GFS minus ERA, RO minus RS, RS minus ERA, and RS minus GFS. And from these 6 equations, you can derive the 6 estimates of the error variances for the different data sets. And this one you've already seen before. That was the first one. And there's no point in spending a lot of time on this in this talk because you can work it out, and you can have this and then you can have the paper if you want. This is the 6 equations. You saw these before, so they shouldn't startle you. And then I highlight the red terms. These are the terms you have to neglect. All these error covariance terms have to be neglected, and it's between errors and RO and ERA, RO and radiosondes, radiosondes and ERA. And not only do they have to be 0, but in a finite data set, even if they are 0 in an infinite data set sample, they will be non-zero if you actually try to compute them. So you need a very large data set to make these red terms that you're neglecting go away, even if the error covariances are actually 0. Now, they're not going to be exactly 0. For one thing, ERA assimilates radio occultation observations. So there's going to be some correlation between RO and ERA errors. But ERA also assumes 26 other observation types, so you'd expect the correlation with any one of them to be small. Nevertheless, there probably is some non-zero covariance. Same with radiosondes and ERA. ERA assimilates radiosondes, so there's going to be some correlation of the errors of radiosondes and the errors of ERA. So some of these terms, there's no reason that RO and radiosonde errors should be correlated. They're totally independent systems, so this term probably is 0. Anyway, you got to neglect these to do the method. And so here you are. You've got RO data sets, you've got ERA, you've got RO and GFS, you've got GFS and ERA, so you can compute the mean square of the differences and get this estimate. You can use this equation and get these using these terms. I said it looks like magic, right? And you can use this. You see why they were skeptical, and so on down the line. If all of these red terms are negligible and the data set is infinite, every one of these 6 estimates would be identical. You can show this by using an error model. But, of course, they're not all 0, and these combine in different ways and that are hard to understand. But you do get 6 different estimates. It also turns out that the first 3 are linearly independent, and the last 3 are linearly dependent on the first 3. But they use different combinations of the data sets, and so they actually give you different answers. So we computed, using these different data sets, the 6 estimates from these 6 equations, and we compared the full 6 set of estimates with the 3 linearly independent estimates and actually found out that they were rather similar. So anyway, this is how you feel after doing this tedious algebra and keep making mistakes. And this is probably how you feel. A few things to worry about: error correlations among 2 different or more data sets. Small sample size, very different magnitude of errors. If 2 of your systems are very accurate and 1 is terrible, then this leads to trouble. So you want them to be roughly, but in meteorology, most of our systems are, I think, meet that, have similar magnitudes of errors. And bias errors in one or more of the data sets. And we have not gotten into the bias errors yet, so we're only looking at the data, the random errors, but still this could probably causes a problem. Okay, so the same procedure can be used to derive 6 equations for the error variances of the other 3 data sets. Remember, those 6 were all RO estimates. You get the same set of 6, but for radiosondes, ERA, and GFS. And I don't show these, for which I'm sure you're grateful. You won't have to see those. So for each of the data sets, there are 6 different ways to estimate the error variances. And I mentioned this before, the first 3 are linearly independent, the other 3 are linearly dependent. And again, if the error covariance terms are all 0, the 6 methods would give identical results. So let's see how this works. Well, Risa's first paper, which was more of a detailed comparison of these different data sets, how they represented the dry layer and the boundary layer and the tropopause and so forth in this tropical Pacific area. She used Guam, which is very near the equator, and then 3 Japanese stations, which we abbreviate as Ishi, Mina, and Nazi, because we can't pronounce these. It's very simple. So we call these Guam, Ishi, Mina, and Nazi for our 3 stations. And then we use the INSEP global forecast system. And the analysis there is the grid spacing is about 28 kilometers. So truth there is a 28 kilometer average. And the ERA-Interim reanalysis, the grid spacing is about 80 kilometers. So it's bigger. Okay. Now, we use the radio occultation data set from the Cosmic Data Analysis and Archive Center. And this equation is an important one. It relates the refractivity to the pressure, temperature, water vapor pressure, and temperature. And from this equation, we can derive the temperature and the water vapor pressure, and from that, the specific humidity and relative humidity, if we have a way of separating out the contributions of temperature and water vapor from this equation for refractivity. I'll get to that in a minute, but I'll get to it right now. There are 2 retrievals for the radio occultation temperature, water vapor, and specific humidity and relative humidity. The direct method, we use the temperature from the GFS model, plug it into here, solve for water vapor pressure given temperature and refractivity. Refractivity is the radio occultation measurement. And so we can solve for E by just plugging in the GFS temperature. That's the so-called direct method. And another method is to use a 1-dimensional variational solution using the ERA temperature and Q as a background and the observed in. It's kind of a least squares minimization thing that you can use the observed in and the water vapor and temperature from the ERA analysis as a background. And these give different answers, especially in the upper troposphere. And we compute normalized differences using the ERA 2007 annual mean at each station for the normalization. So the normalized differences are data set 1 minus data set 2 over this 2007 mean, which we call CLIMO. And you'll see that makes these differences a similar order of magnitude at all levels. Just briefly, some of you may not be really familiar with what a radio occultation is, so I don't want to spend too much time on this, but radio occultation is a active remote sensing technique where radio waves from the GPS satellite pass through the atmosphere, and as a low Earth orbiting satellite, in this case sets behind the Earth, is occulted by the Earth. These rays scan through the atmosphere until the Earth obscures the line of path, and because of the density of the atmosphere, the variation of density in the vertical, you get a change in frequency as the LEO sets relative to the GPS satellite, and that can be used to derive, jumping all the way to the bottom here, the refractivity, which is a function of the density of the atmosphere. So it's a very powerful technique. It's an active remote sensing technique, and it gets, because of that, and because of this limb scanning, vertical limb scanning technique, it produces very high vertical resolution soundings. And I guess the important thing is the radio occultation signal, the refractivity that it gets, is sort of a weighted average along this like pencil-like path. Because if you look at that cartoon again, you're measuring in some sense, the average effect of this radio wave on this radio wave of the density variations along a horizontal path. So it's not a point measurement. And that's important because it gets to what truth is. The radio occultation observation is something like a weighted horizontal average with a scale of about 200 to 300 kilometers and a vertical scale of about 1 kilometer. Kind of a weighting function like that. So actually the radio occultation observation is somewhat more like the model horizontal resolutions than they are a radiosonde observation, which is a point measurement. So you've got a point measurement, you've got this kind of measurement, you've got the model averages over grid spacing, and that all gets to what truth is, and it gets into representativeness errors. But in fact, representativeness errors are embedded in these error estimates. I'm not going to get into that, but just to show you that radio occultation can be very important in operational weather prediction. This is a figure from the ECMWF in June 2011, 4 years after the cosmic satellites were launched. And you can see at this time, radio occultation was basically tied for second in terms of impact on the ECMWF forecast scale. AMSU-A, microwave sounding unit A, was actually the most effective in this study. And these are both infrared, high-resolution infrared sounders, and this is aircraft reports. But radio occultation was actually essentially tied for second and through fourth in this particular study. So radio occultation can be quite beneficial. All right, now back to our study. Sample size is important, so I show the sample size for Mina, one of the Japanese stations, and Guam. These are number of co-located measurements, pairs, GFS, ERA, GFS, radiosonde, radio occultation, and so on. So you've got to have pairs of all these data sets at the same time and space. So the first thing you have to do is co-locate all these different measurements. And we were able to do this. We got something like 800 in the upper troposphere, and those numbers dropped off as you go into the lower troposphere, primarily because of radio occultation. Some of the observations were lost and did not penetrate far enough down. So by the time you get down near in the boundary layer, you're down to 200 co-located measurements. And from some other studies we've done, and I'm not going to show today, but I think recently you'll show some of this on Friday. This is a pretty small number, and we get large sample size errors for this number of sample size. 800 is much, much better, and in some of our error model studies, we actually get over 1,500, about 1,500, and that's good. But that gets back to the caveat. If you're going to try to use this method with only a sample size of a dozen, it's not going to be very reliable. You got to use get a large number of measurements. And here's what the soundings look like for Guam and MENA. Just to give you a physical interpretation of what's going on. The Guam sounding, the mean sounding is this black line. This is specific humidity, grams per kilogram. So Guam is near the equator. So the annual average is about 17 grams per kilogram. Decreases rapidly with elevation. The blue shading is the Guam standard deviation over this year. And this for the Japanese station, the mean profile is drier, and the spread is greater because it's subtropics, so it gets some really dry and cooler air in the wintertime. Temperature shows less variance, but this is a temperature profile for Guam. The tropics is very similar throughout the whole year. Here's MENA. So that just kind of gives you an idea of the physical soundings for what we're dealing with. This gives you another idea, just a comparison of individual soundings from the 5 data sets. Specific humidity, this is at Guam, all these are at Guam. So this particular day, this particular set of observations, the red is radiosonde, the dashed is GFS, the solid blue is ERA, and then radio occultation, the 2 radio occultation profiles, retrievals, give this profile. And relative humidity is shown here for the different profiles. Temperature, they're much more similar, and refractivity, the different profiles are shown there. So it's these differences, these relative differences between these data sets that go into the calculations for the error variances. I just wanted to briefly mention the apparent error method, because that's one of the methods we use to show that this three-cornered hat method was not nonsense, at least. And this is a paper, 2 papers by Bill Kuo and Shuya Chen, who some of you may know, estimated the RO error variance of refractivity using the so-called apparent error method. In the apparent error method, you take the observations you have minus the forecast of that observation. Then you just do this simple squaring, you neglect the covariance terms again, and you get the standard deviation of the observational error that you're interested in is equal to the, well, that's just the square root of that. So anyway, this is the equation you use to actually compute the apparent error of x obs. It's x obs minus equals the mean square of x obs minus x forecast. Minus the error variance of x forecast. This is a very simple method compared to the 3-hat method, but you must know the error variance of the forecast from an independent source. So that's why it's not as powerful a method as the 3-corner hat method. However, if you know the error variance of the forecast, you can then easily compute the error variance of the observation. And so here's some of the calculations that they did. This is from Shuya Chen's paper. In the winter, in the summer, over a very large area of the Pacific, and it shows that the black line is the, make sure I get this right, is the apparent error. So this is what you actually, they actually compute. And then here's the error of the forecast, and then you subtract this from this, and you get the error of the estimated error of the radio occultation observation. The reason this doesn't look like it's a subtraction is because you're really subtracting variances, and then you take the square root. Anyway, this is what they get, and this is a very common estimate of the error variance of radio occultation, this thin solid line, and it shows a value of between 2 and 2.5% near the surface, decreasing to under 1% in the middle and upper troposphere, where the RO is most accurate, and then increasing again above into the stratosphere. And you see that in the summer is similar. They're using this kind of profile in numerical models when they assimilate radio occultation data, because you have to assume something about the errors of the data you're assimilating. So we use their apparent error estimates and compared our estimates using the three-cornered hat method, and now using ERA as substituting for the forecast. And I'm not going to go through this math, but you can see that our blue curves, which is the three-cornered hat method, have very similar magnitudes and profiles compared to the apparent error slide I showed you just before. The error is between 2 and 2.5% on the surface, decreases to about 1% or a little less in the upper troposphere, and we didn't go high enough to get the high enough into the stratosphere to get the return of the increase of the RO error estimate from the three-cornered hat method. But these are four different stations. This is Guam, this is Ishi, this is Mina, and this is Nazi. And so it looks like roughly the same kind of profile. Magnitude and shape is the same. Totally different methods, and so we say that this is partially verification that the three-corner hat method works. Okay, so now a few slides showing the actual results. And this first slide shows the estimated error variances of specific humidity using the three linearly independent equations at Mina, one of the Japanese stations. And we have here we have they're all specific humidity estimates. The first two plots are the different RO retrievals, the specific humidity. The RO direct using GFS and ERA, and radiosondes are shown here. Remember, there's three equations for each one of these estimates. So you got actually a blue dash and a dotted line. There's three curves here. These are the three equations. So very similar. And then here's the results from the three equations using the 1D var estimate of specific humidity. You see that they diverge from the direct method above about around 600 hectopascals, and their errors decrease. So what we're seeing is that this is a very realistic signal, because the direct method of computing specific humidity, we know that radio occultation, the signal due to water vapor is very small in the upper troposphere. So you can get very large errors if you just assume a temperature from some other independent data source. But if you use the 1D var, you constrain that water vapor retrieval by the first guess, which in this case is ERA, and so that error actually decreases. So this is very plausible behavior. In the lower troposphere, all the three equations for the two radio occultation retrievals are very similar, as you can see. So the fact that these two methods and the three equations for each method give very similar results, we think is a indication of the power of this method. This is radiosonde error variance of specific humidity. There's using the different data sets, and there are actually, believe it or not, 6 curves here, but they overlap so much you can't distinguish them all. And again, it's the different combinations of the data sets and the three linearly independent equations. So the fact that these all give essentially the same answer, I think, gives a lot of credence to this method. This is GFS error estimates, and this is ERA, specific humidity error estimates. So you can see from these that, that the ERA has by far the smallest errors of specific humidity. And but that's not really the point of this. The point of this is not to find the best, but the point is to show that you get differences, meaningful differences between the error estimates of the different data sets. I saw that one, okay. And here's relative humidity. These just toggle back between relative humidity and specific humidity. The fact that the relative humidity curves are also very coherent, they're very close together, and you get, it's kind of remarkable because relative humidity, of course, depends on errors of water vapor and temperature. And the fact that you're getting these very consistent estimates of the error variances for these different data sets for relative humidity, I think, is an important conclusion. And here's temperature. Temperature, everybody measures temperature pretty well. The radio occultation estimates, it's a little bit confusing here because we're using temperature directly in some of the calculations, so maybe don't pay too much attention to that. But here's the radiosonde temperature error variances, about between 0.1 and 0.2% squared. So take the square root of that to get the standard deviation, and you're down to a pretty small a fraction of a percent for the radiosondes. And this is GFS and ERA. Everybody, they all do pretty well on temperature. Water vapor is a severe test. And here's refractivity, and I won't spend too much time on this, but here again are the refractivity variances for RO, and you see it's that very, you have to take the square root of this to get to compare with the standard deviations we had before, but you can see it's similar, maximum values in the lower troposphere decreasing, radiosonde, GFS, and ERA. And you can combine all this by plotting the mean of these three equations for each of the variables at one location. This is at MENA. So in this slide we have, for example, the average variance of the error of specific humidity from the three equations for the different methods. And this is, do I have the, yeah, the key is down here. So this one is radiosondes. This one is radio occultation direct. This blue is radio occultation 1D VAR retrieval. This is GFS, and this is ERA. So this is specific humidity, relative humidity. Again, ERA is clearly the smallest error. GFS is next. And then the two radio occultation methods diverge above 600 hectopascals, and the radiosonde is the has the greatest errors in this data set. Temperature, small, a lot of very small numbers. This is the error variance of 0, 0.1, 0.2, 0.3 Kelvin. So the biggest error is, in this case, error variance is RO, and that's this blue line, and then radiosondes over here, and GFS and ERA, and refractivity, similar thing. ERA is the smallest, GFS, RO, and radiosondes. So now I think my getting close to the end here, but the last slide is just to compare these mean figures at the 4 locations. So there's Guam, Ishi, MENA, and Nazi. And just looking at the point here is that you get similar profiles, similar estimates at these 4 independent stations using different radiosondes, and of course there are different locations. But again, you see that the ERA has the smallest errors, variances at all 4 of these locations, then GFS, RO, RO1DVAR, RO direct, and then radiosondes. And that pattern is similar. So we claim that you don't get this stuff by accident. If these errors were highly correlated, the data sets were highly correlated, you would see junk on these figures. You would not see these nice coherent profiles that clearly distinguish the different data sets. And from what data we have for comparison, these agree pretty well. So in conclusion, we claim, and we'll see what the reviewers say, that this three-cornered hat method can be used in atmospheric sciences. As far as we know, it's never been used in atmospheric sciences before. None of these threads that go back to the 74 or the 98 paper use this method in atmospheric sciences. Oceanography, ecology, leaf area index, and clocks, atomic clocks, and GNSS clocks, well, same thing, use the method. But I've never seen one in atmospheric sciences using these methods, which is kind of surprising, because we, atmospheric sciences, are very interested in data sets from different observations and different models, and this seems to be a good way to compare the errors of different data sets. You can also, well, I'm not going to get into that because I don't want to have to prove it, because the work is still in progress. Second bullet, the errors are considerably different for the data sets, and we found that the ERA-Interim seems to have the smallest errors in this study. And I think that's reasonable because ERA uses every data set available in 2007. Aircraft data, aircraft reports, radiosondes, radio occultation, surface observation, surface pressure, infrared sounders, microwave sounders, and they have a very modern, at that time, data assimilation system. They do quality control of all these observations after they come in, so they use observations that don't come in time for the operational forecast. So you would expect that ERA-Interim is probably the best you can do in terms of global analyses of these variables. And Sean Healy may be skeptical. This is taken at that breakfast thing, but he liked the fact that ERA was small, even though he didn't believe it. He was one of the more skeptical. And that's the end of the three-cornered hat story. And if you look up three-cornered hats, you find a lot of pictures of the three-cornered hat. So thanks for your attention. I'll be happy to try to answer any questions.
Okay, questions?
Yeah, it looks like in your analysis you used 4 estimates of the variables. Is that correct? 4 techniques or whatever?
Five data sets, actually. There was 2 of RO, two retrievals, and GFS, ERA, and radiosondes.
So I'm wondering, is there a relationship between the number that you use and the number of equations?
No.
You always have 6 equations or something?
Yeah, actually there can be, and you're getting into, you can actually use, this can be called the n-cornered hat method, where you have n data sets, not just 3. I think what we're doing is we're comparing 3 at a time. So even though we have 5 data sets, we're only comparing 3 at a time to get these error estimates.
Okay, so when you have 3 at a time, then you have, 6 equations for that set of 3? Or how does that work? I'm still a little confused.
Yeah, so are we.
And I was also confused about why it's called three-cornered hat.
Well, because it's 3 data sets.
Okay, that's for the 3 data sets.
Yeah. So, see if we had these, here's RO, that's 1 data set. ERA is 2, GFS is 3. So these first three equations, well, actually all 6 of these equations use just 3 data sets, right? No. We got 1, 2, 3. See, we all get confused. 4, right. So we've got 4 data sets, and you get 6 equations. If you only had 3, well, you'd probably only get three equations.
Okay, so there is some relationship between the number of observations and the number of equations.
The number of data sets and the number of equations.
Yeah, okay.
The number of, and again, these 3 are linearly independent, and they do use the 4 data sets, don't they? RO, GFS, radiosondes, and ERA. Have to think about that some more. You can. This is why this is why I put that next slide in there. Yeah, so am I.
Yeah, good talk, Rick. I have a couple questions. The first one, in definition of collocation, did you interpolate all the data sets to the location of the station? And number 2, did you look at all at the biases, not just the variances?
No, we did not look at the biases. The biases are all in here. These are just the differences of the data set, but they're all interpolated at the same location. Yeah.
So now that you have data, did you go back and calculate those covariances to see if they really are closer to 0?
Well, you never know. You can't.
But since you put those at your 4 points, couldn't one actually calculate those terms at the 4 points and then, really provide evidence that it was reasonable to cross those out?
We get the error variance of RO, we get the error variance of ERA, but we don't get the error covariance. So I don't think we can compute this from our data sets. We did, and Reese is going to talk about this Friday, use an error model to generate fictitious simulated data sets with known errors put on it so we can calculate these terms explicitly. But whether the error model is realistic or not, I don't know. But I don't know of any way to go back with our results and estimate these error covariance terms individually. I have to think about that some more, but we get the error, we get the variance of RO, error variance, and we get the error variance of ERA, but we don't get the covariance estimates. So that would have to come from some different method. In fact, that's the hardest part about writing this paper, is proving or indicating that these are 0. But if they weren't 0, and you're adding them and subtracting them in all these different ways, you would not find such agreement in these 6 sets. So it's kind of the proof is in one of our reviewers at ECMW. So the fact that these are also coherent indicates that these are not wildly different from 0 and different from each other, in which case you'd get 6 wildly different profiles. The fact that every one of these agrees within a small margin. And that small margin is the effect of these error covariance terms combined in different ways. So the aggregate effect has got to be small because the spread about the mean of these 6 estimates is small. I tell you, it's moving around pretty fast here. And that's the kind of question
sorry, very bad. So actually, ERA is a little bit special because ERA, although they're using multiple either radiosonde or whatever data altogether, but if they're using RO as a benchmark, that means everything actually may be corrected to RO. So it's not like they in one specific location they're using all the data. Maybe other are relatively random, but RO itself probably is highly coherent in that way. So there's one comment. And then second comment is if we have 3 different types of observation, independent observation, RO, radiosonde, and maybe something else, maybe airs or whatever, then maybe it will be easier to explain then in internal some other model data, they have a model error plus observation error, and then they simulate all the 3. I just say it. I don't know if that would be more independent or easier to explain.
The first question, I don't think ERA was preferentially affected by RO in 2007. There were many fewer RO observations than any of the others, and they're using all the infrared, and they're using everything. They're using radiosondes at these locations. These are at radiosonde locations now. Remember, the RO locations are scattered around, and they have to be corrected. But I think ERA is using something like 26 different observation systems. And I don't think it's, they're probably highly, if they're correlated with anything, it's the probably radiosondes. Because this is at the radiosonde location. You expect the radiosonde to affect the ERA most at that station. So I suspect that it's these terms that are most correlated. But still, you know, I asked NWP experts what they thought the correlation of errors would be, and they think, I don't know, one person said 10%, 0.1 correlation coefficient, 0.2, but not highly correlated, because if they were highly correlated, then these would all give different answers. So the fact that they all give a very narrow spread for these 6 estimates indicate that these terms are not wildly different from 0.
Okay. Any other questions?
It's tough. I go back to this one as my should have.
Wondering, could you comment on the 3 requirements you mentioned? Big data set, small bias errors, and error can't be too much different from each other. How do you quantify those numbers for any given data set?
Well, we did this error model study because we could. Well, actually, we could do this. We could quantify it by either doing 2 or 3 years of this study instead of 1 year, or just use half the year. And did we do the half a year, Risa? We did. We've done it. We've done a sample size with the error model and find that 1,000 is good. 500, you start getting more noise. 100, started getting more noise. But that depends on the error model. So this is heuristic at this point. I'm thinking that you'd like to have at least 1,000 pairs, and you're probably in fairly good shape. If you're down to 100, it starts to get questionable. But as I was talking to you before, if you had 3 radars set up at the same spot, looking at the same, and ran them for 5 days or 10 days, you'd have thousands and you'd have a tremendous 3 radars to get the errors of each one. So it'd be a really neat experiment to do, and you got to do this with remote sensing. You can't launch that many dropsondes or in the field program because you're not going to get 1,000. Well, maybe you might. I don't know. If you go for 3 months and you're launching 10 a day, I don't know. You might get 500.
Okay, I think we'll close here, and thank you again, Rick, for a very interesting seminar. We know where to find you, so if there's any more questions, please come up and let's discuss.
If you want the paper to see the magic behind the smoke and the mirrors, I can send you the paper. And I'd love to see some other people try the method using different data sets. And see, because it's never been used in atmospheric sciences before. That's the point.
The AMT paper is open discussion, is that right?
Yes.
You comment on that.
Yes. Only make good comments.
Okay.
Yeah.
Thanks again,
Okay.
Rick.
Thank you.
Thanks.